had helicopters out there. We've had a couple of cutters. As long as the Coast Guard feels there's a probability that they're still alive, we're going to continue searching.
The explosion of the Deepwater Horizon oil rig in 2010 launched an intense investigation into drilling practices and resulted in lasting ecological damage. The initial explosion caused 11 deaths, and the subsequent blowout released 134 million gallons of oil into the Gulf of Mexico. But could this tragedy have been prevented? The rig was equipped with numerous safety mechanisms. However, a series of oversights and system failures resulted in disaster. After burning for 2 days, the Deepwater Horizon sank into the ocean, but oil continued to spill out of the well for another 85 days. Why did the many layers of safety protocols and the emergency stops fail? To understand how this happened, we need to examine the months leading up to the disaster and the engineering challenges after the blowout preventer failed. Deepwater Horizon was a massive, semi-submersible, offshore oil drilling rig. Owned by Transocean and operated by BP, this dynamically positioned rig began drilling at the Macondo prospect in February 2010. The Macondo well was a challenging site that was causing massive delays in BP's schedule, each day of operation costing over $1 million. While the rig was deemed a model for safety by the Minerals Management Service, there were a number of citations before 2009 for not meeting safety, pollution, electrical, and mechanical regulation. On the evening of April 20th, 2010, Deepwater Horizon was in the final stages of drilling the well in the Gulf of Mexico. Up until this point, there had been several setbacks, including lost circulation events where drilling mud leaks out of the well and kicks where high pressure gas enters the riser pipe. However, work continued as there was pressure to complete the project and move on to the next site as soon as possible. This pressure resulted in a series of critical decisions and poor judgments that contributed to the eventual blowout. For example, to save time, only 6 centralizers were used to place cement along the drill casing instead of the usual 21 centralizers that were recommended to ensure uniform cement distribution. Based on lost circulation events that indicated that the rock formation at the base of the riser pipe was fragile, several corners were cut in attempts to reduce stress on those rocks, using foam cement, which has a reduced density, reducing the pumping rate below normal levels, using cement volumes below BP's guidelines, and shortening the time allowed to equilibrate the viscosity of the drilling mud. The critical problem here was using foam cement because it is not guaranteed to remain stable, which can result in abnormally low mechanical strength. Despite the knowledge of this potential for instability, operators went through with the decision to use a foam cement slurry. And despite changing several operating parameters such as the pumping speed and the materials, testing to make sure that the cement was properly installed was overlooked. Additionally, even though BP had made changes to procedures for disconnecting the rig from the well only 2 weeks prior, there had been no risk assessment of these new procedures. Before disconnecting Deepwater Horizon from the well to switch it out with the rig that would complete the hydrocarbon production process, pressure tests needed to be conducted to assess the structural integrity of the riser pipe that ran from the bottom of the ocean up to the rig. While the positive pressure test was a success with no issues, the negative pressure test, where seawater displaces the drilling mud in the riser pipe, showed extremely high pressures. A high pressure reading was intended to alert the crew to integrity problems both with the cement casing along the riser pipe as well as with the blowout preventer just above the well. The blowout preventer is a device that connects the riser pipe to the top of the well and contains mechanisms to stop or start the flow of fluids across a series of valves. Despite conducting the negative pressure test 3 times and getting the same worryingly high pressure readings, it was decided this high pressure reading must be incorrect, and the order was given to open the blowout preventer to begin displacing the drilling mud in the riser pipe with the less dense seawater. Just as the negative pressure tests had indicated, pressure quickly rose in the riser pipe as drilling mud was replaced with seawater, and there was a rapid increase in flow rate up from the well. However, these indications that something was seriously wrong were ignored. Suddenly, an eruption of seawater surprised the crew. The seawater was soon followed by drilling mud spilling onto the deck and methane gas released into the air. At this point, still, the well could have been closed by engaging the blowout preventer. However, workers only attempted to close the annular preventer, which had little effect. The gas built up quickly and, ignited by motors on the deck, created a fireball explosion that caused chaos aboard the rig. But it was not only the mechanical failures that caused this disaster. Poor regulation, human error, and questionable management decisions are what sealed the fate of the Deepwater Horizon. BP failed to keep up with the maintenance and regulation of the rig in favor of saving time and money. Transocean failed to notify the crew of a similar incident, which occurred only a few months prior, from which they might have learned to spot the warning signs of a blowout or to check the blowout preventer and emergency systems for maintenance. Additionally, the pressure to complete the project, which was already weeks behind and millions over budget, led to corners being cut and warning signs ignored. Additionally, the Mineral Management Service was not equipped to oversee or properly regulate the complex systems involved in deep water drilling. Workers on the rig at the time of the disaster recall being unsure of how to proceed and unfamiliar with the procedures for such an emergency. For instance, the alarm systems needed to be activated manually, relying on human judgment, and operators were not taught the full, very complicated procedures. Workers on the rig did not know the situation they were in, nor how quickly it would escalate. And there was also a fear of overreacting, the fear of damaging equipment, of getting further behind schedule, and even of disrupting other crew members at that time in the night. As drilling mud is spewing out of the pipe, workers on the rig attempted to activate the blowout preventer. This device was specifically designed to prevent an oil spill in this type of disaster, but the blowout preventer failed. In a final attempt to stop the oil spill, the crew tried to activate the emergency disconnect system, which would close a blind shear ram to seal the well and disconnect the rig. However, the system did not respond. There was likely already electrical damage to the system. Still, the automatic shutoff should have been triggered to seal off the well. Later in the investigation, it was revealed that the emergency disconnect system did not work because of dead batteries and defective parts, resulting from the neglect of regular maintenance. The initial explosion and subsequent fires killed 11 workers. The rest of the 115 workers evacuated to a nearby ship and watched as the rig burned. Firefighters on the water tried to put out the fire on the rig, but after 2 days of burning, the Deepwater Horizon sank into the ocean. But this was just beginning of the disaster. Oil, pouring out of the well at a rate of 600,000 barrels per day, continued to spill into the Gulf for 87 days, causing ecological damage to marine and coastal habitats from Texas to Florida, eventually affecting a massive area of 68,000 square miles.
I want to update the American people on the status of the BP oil spill, a catastrophe that is causing tremendous hardship in the Gulf Coast.
Efforts to stop the spill started immediately. Remote underwater vehicles tried to repair the existing blowout preventer, but had no luck. The riser pipe had been bent and the valves were not able to properly seal the well. On May 2nd, drilling began on a relief well, which would connect to the original and allow the well to be sealed with cement. However, this would take at least 2 months to complete. Next, engineers attempted to place a cofferdam, a large steel containment dome, over the well to contain the spill and then funnel oil into a pipe. However, methane gas hydrates quickly clogged the dome with ice crystals, at which point it began to fill with high-pressure gas, causing the cofferdam to rise like a massive steel balloon and forcing the engineers to abandon this plan. The next daring idea was to pump drilling mud along with junk shots of debris such as rubber waste and golf balls in an attempt to plug the lines in the blowout preventer. But these materials could not overcome the pressure of the oil and gas spewing out of the well. Attempts to slow the spill by inserting a tube into the riser so that some of the oil could be siphoned off and collected worked, but there were still thousands of barrels of oil and gas leaking into the water every day. Finally, a small blowout preventer cap was designed that could fit over the original blowout preventer and hopefully seal the well. And at last, when this cap was lowered into place, the well was sealed and the oil spill stopped on July 15th, but this was only a temporary solution. There was fear that the cap would dislodge or that it would cause irreversible damage to the blowout preventer or to the structure of the Macondo well itself, which would make it nearly impossible to reseal. It took until September 19th for the relief well to be completed, at which point cement was poured into the secondary well, permanently blocking the spill. The Deepwater Horizon disaster had lasting environmental impacts, as well as impacts on regulation of drilling practices. The engineering failures, including neglected maintenance, inadequate testing, ignored warnings, and unsuccessful attempts to stop the leak after the explosion, made this incident the largest oil spill in marine history. Transocean paid $1.4 billion for violating the U.S. Clean Water Act. BP has paid $2.4 billion with additional penalties pending. And as of 2018, $65 billion has been paid in settlements to those affected. But this does not make up for the negligence on the part of Transocean, BP, and the lack of proper drilling regulations that led to this catastrophe.